So what we just discussed gives the full form of the neighborhood predictor, or at least our full form of the neighborhood predictor and what we'll be doing. And so basically, if we just apply that scheme of taking the error and adding it to the baseline, the neighbor's error, and then adding it to the baseline prediction, we'll come up with this table as the neighborhood predictor. And so I just wanted to thought it would be good to just formalize the discussion on the neighborhood predictor, just so you have sort of a scheme to follow. And you can obviously refer back to the example and just go through that too, but just so we can just walk through this really quickly. For the neighborhood predictor, basically you take user U and movie M, and the first thing you do is you find M's nearest neighbor, right? So say that's movie N, right? So if it's movie 5, we might have the nearest neighbor being movie 3, right? So N, and we see whether U has rated N. So if it's some user, right, we're just looking in this users row right now, and we have M and N over here maybe. So we see first whether or not there's an entry in N that we can use. If so, right, if he has, so we'll say that he has. If he hasn't, then you just keep the rating the way it is and you don't change it at all. But if he has, then you ask yourself the next question. Then you look at the table of correlations between movies and movies. So you look from M to N, and you try to see what that correlation value is. So if the correlation between M and N is positive, then we add the baseline error for U and N to the baseline error for U, to the baseline prediction for U and M. So basically take the value that we had for the baseline predictor, and then we add whatever error there was in for U and N. And if it's negative, then we subtract the error that we see for U and N and from the one that we see for U and M. And that's how we change it. So we add if it's a positive correlation, we subtract if it's a negative correlation. But remember that we're adding baseline errors and subtracting baseline errors to the original baseline because we're augmenting the original predictor, so it's incremental on that. So now this is a little hidden right now, but so for the RMSE, let's try to figure out what it was for the test now and what it is for the training set. So we want to see how much better we're doing now that we've done the entire neighborhood predictor than what we were doing before. And so we'll do again for just the test set. We have the 4, 2, 5, 3, and 4, and we're comparing that to 2.8, 1.5, 5, 3.33, and 3.27. So we'll take the square root of the sum of the squares again, 4 minus 2.8 squared plus 2 minus 1.5 squared plus 5 minus 5, which will just be 0 squared, plus 3 minus 3.33 squared plus 4 minus 3.27 squared. And we divide that by 1, 2, 3, 4, 5, because there's 5 of those terms again. And if we do that out, I'll just write out here the terms again. We have 1.44. We have 0.25. We get 0. We get 0.11. And we get 0.53. Divide that by 5. Do that all out, and we get 0.6826. So this is the RMSE for the test set is 0.6826. And then for the training set, we can similarly find the RMSE to be 0.4660. So now if you compare those with the values that we had back in the just the simple raw averaging that we did in the beginning, this is an improvement of 33% about, and this is an improvement of like 68%. And that is about 5 to 10% improvement. On the test set, it's about 5% improvement. On the training set, it's about a 10% improvement over what we had for just the baseline predictor. If you remember those values before, they were like 28 and then 56 or something like that. And so we are doing better. But again, you won't always do better, but you expect that you will do better. And in this case, we've seen that we do better when we add this neighborhood prediction on top of it.